All right, so Unit 3 exam review here, guys. We'll go over the key stuff, key concepts, skills you're going to have to demonstrate. Okay, give you an outline of the exam, what to expect. It's kind of the same as always, some multiple choice and some written response. Okay, but we'll go over that in a little bit more detail here as we go along. So, first thing we covered, types of and forms of energy. Okay, that's going to be multiple choice. Okay, so I might give you a question like, a downhill skier is nearing the bottom of their run. Which would best describe the type of energy they possess? A, chemical. B, potential. C, kinetic. D, mechanical. Which one do you think? Mechanical. Mechanical is the best answer. Okay, they might have some potential. They probably have some kinetic. Okay, but they probably have some of both. And if they have either one, they have mechanical. That's what makes mechanical the best answer in that situation. It is the one that is true no matter what is true about potential and kinetic. If they have either one or both, they have mechanical. Okay, that's one of those tricky questions, okay, that has a best answer, right? And multiple choice is always about picking the best answer, okay? All right, so know that one, okay, just for multiple choice. Also know your systems, open, closed, and isolated, okay? Easy multiple choice question there. Okay, open system can exchange energy and matter. Okay, closed system can exchange energy, isolated, neither. Right. Okay. Okay, and then know about thermodynamics, heat engines, and heat pumps. That was all in lesson 2. Okay, just know how they work more for multiple choice than anything else. Okay. Okay, perpetual motion machines. Here's what you need to do with those. Can one exist?
No.
Okay, even if it could, what's the problem with it?
There's always an exchange of it.
You can't do any energy out of it. It's just moving.
Right, it can never do any work. Right. Okay, probably good to understand that. Okay, understand kind of why a perpetual motion machine can exist, because it's always going to lose energy to the surroundings. Okay, any conversion of energy is never 100% efficient. Okay, and also that even if you could make one, it would be completely useless, right? Because it could never do any useful work. Okay. All right, moving on from there. Okay, scalar and vector quantities. Where am I going to test that? Multiple choice or written response? Both. Okay, there could very likely be, a multiple choice question, that says which of the following is a vector quantity or which of the following is a scalar quantity. Certainly I could do that. Where it's most important is in the written response. Being able to remember which quantities are vector and which are scalar is crucial because you solve for vector quantities in different ways than you solve for scalar quantities. Direction matters. Okay? But even more importantly than that, you need to know whether a question is asking you to solve for a vector quantity or a scalar quantity. I'll give you an example. Let's say I give you a question like this. A car is traveling up a hill when it runs out of gas. Okay? It is moving up the hill at 3 meters per second when it runs out of gas. It begins to accelerate down the hill at 1.5 meters per second squared. What is its velocity after 6 seconds? Okay, would you be able to calculate that? Yeah, it's just an acceleration problem. What does your answer need to have on it?
Direction.
Right, down the hill, specifically as a vector. If I do that on the test, I can guarantee 2/3 of you will forget to put a vector on Do you know why I can say that?
Because you've done it before.
Yep. Done it before. 2/3 was not the biggest amount of people who ever forgot. I once had a class of 25 people where I only had one person remember to put the direction on. 23 of those 25 people had the right number. They had done the question entirely correct, but got 4 out of 5 because they did not write down the hill on their answer after getting exactly the same spiel I just gave you.
I find it funny that one guy got it wrong. Just like one. Because he said 23 out of 25.
Yeah, I know, one person did get it wrong.
Poor guy.
That was an AP class. Just putting that out there.
I was like, oh, I'll take one for the team. I'll be the one. Got it.
All right, so scalar and vector quantities, just as a quick review here. Some of our quantities that are scalar are speed, distance, time, energy, work, okay? Those are all scalar quantities, okay? Vector quantities, velocity, displacement, acceleration, and force. Okay? Although for us, force being a vector quantity has never been an issue. We've never had to use vectors with force. Okay, B equals D over T. Gonna have to use that? Where's that gonna be? Multiple choice or written response? Probably multiple choice. It's a pretty easy calculation. Okay, I'm not gonna waste a 4-mark written response item on a B equals D over T question. Okay, now that said, it's possible you might have to use that with maybe a graphing question, okay, in a written response item. Okay, but there'll be no B equals D over T problem for its own sake. Okay, so multiple choice on that one. Okay, graphing. Absolutely, positively, the single largest set of marks on this exam. Okay, there are several multiple choice questions involving interpretation from graphs. And there is one of each type of graph in the written response. So one position versus time, one velocity versus time. Where is a good place for you to find the type of question I will ask on those graphs?
The practice test.
Nope. Well, I mean, there's one on each on the practice test, but I was thinking of something you've already done and I've already handed back to you. The labs, yeah. Okay, you look at the analysis on your position versus time and your need for speed lab, that's what I'm gonna ask. Okay, now, there's a good chance that both of them are not just a linear function, okay? There's a good chance that one of them might be kind of an irregular graph, right? But your graphing skills still apply, okay? Being able to calculate the displacement and the distance and the speed and the velocity from a position versus time graph, okay? Definitely important, okay? Being able to calculate acceleration, displacement, distance from a velocity versus time graph, okay? And being able to interpret what's going on both kinds of graphs, okay? So if I show you a graph, a position versus time graph, let's say, okay, that looks like, okay, so it's a position versus time graph. What is that object doing?
Accelerating it.
Okay, you guys better go over your graphing. This is a position versus time graph. What does acceleration look like on a position time graph?
A curve.
A curve, is that a curve?
No.
Okay, what is going on in this graph?
Constant speed.
Constant velocity in
A
a negative direction, okay? All of that would be important. Okay, if you just said constant speed, if this was a multiple choice question, and A was constant speed, and B was constant velocity in a negative direction, which is the best answer?
B.
B, yeah, B is the best answer, right? Because constant speed could be the other way, right? This, the only one that is definitely always this would be constant velocity in a negative direction, best answer. Okay? All right. I could also give you a graph, maybe a velocity versus time graph. Okay? That looks like that. Okay? What's the object doing in the first part? Traveling at a constant velocity. Okay? What's it doing in the second part? Accelerating in a negative direction. Okay? If 1, 2, 3, 4, at what time does the object change direction?
2.5.
Right there. That's where it changes direction. Right? It changes direction there. It is traveling forwards here and here. Then its velocity becomes 0 for an instant, and then it starts to travel backwards. Okay, graph interpretation looks like something we need to work on over the weekend. Okay? Those are definitely the kinds of things I might ask. Or I could use this, say, let's say without this part, and say calculate the total distance traveled. How would you do that?
Make two shapes.
Right, make the two shapes, find the area under the lines, average velocity times time. Okay? All right, things like that. The other thing, y equals mx plus b. Okay? One of the two graphs is going to be a linear function with an equation. All right? You will be asked to calculate things using that equation. Okay, so what is y when x is this? What is x when y is this? Okay, just like you were in the analysis of both of your labs. All right? So definitely know how to do that. Okay, so the 2.5 here. If this was on a velocity versus time graph, what would this line look like? Where would it start?
38. 30 meters per second on the y-axis.
Mm-hmm. And then it would go up or down. What's the acceleration on that graph? Negative 2.5 meters per second squared. Okay, all the kinds of things you'd get asked on the test. Okay? All right, so graphing, definitely big. Oh, I left myself space to draw all that, and then I drew it up top. All right, acceleration. Know what it is. Okay, there could be a really simple calculation in the multiple choice. Okay, but there's definitely acceleration in the written response. Problem solving, just like what you did on the worksheet in class. Okay, just like problems from the workbook. In an acceleration question, what are some trick words that I might use? Okay, rest. What else? Falling. Something's falling. What am I telling you? Right? Last one. Dropped. Starting at 0. Right. If I say something is dropped, its initial velocity is 0. Okay, so little word tricks, okay, that I can use.
With falling, would 9.81 be acceleration, or would it be?
Yes. Yeah.
Not velocity?
Okay. Work energy theorem. All right, we just did that. Okay. There could be some multiple choice questions about your understanding of the idea and of the concept. Okay, what work is. Okay, maybe some like real world examples of work being done and changing certain types of energy. Cool, question?
I'll just ask you, is it EI equals EF?
No, that's conservation of energy. Work energy theorem is this one.
Oh, yeah. Change it. Right.
Okay, so if I give you an example like what you did in your lab the other day, okay? A rubber band is stretched, 20 centimeters. Which of the following is true? A, the rubber band has no energy. B, work has been done. C, the rubber band has kinetic energy. D, blah, blah, blah. I can think of a fourth one off the top of my head. Which would it be? Work is being done. Okay, B, right? Because the other options were it has no energy or it has kinetic energy. A stretched rubber band does not have kinetic energy, it has elastic potential energy. Okay, that wasn't one of the options, but work was done is one of the options, and it's true. Okay, so little things like that to just test your understanding of work and energy. Okay. All right, and then, in the written response, obviously you're gonna have problem solving. Okay, I told you this the other day. You're gonna have one work energy theorem problem that deals with a change in kinetic, and one work energy theorem problem that deals with a change in potential. How do you tell the difference?
One of them has energy in it, like it was there first.
One's gonna be a change in height, the other.
Okay, they'll both have force in it. One will be a change in
Height.
and the other will be a change in velocity, right? So kinetic involves a change in velocity, potential involves a change in height, okay? And they'll have force in it, or you'll be asked to calculate the force, okay? Or they'll outright say this much work is done, okay, or something like that. Okay? And then after that, we had conservation of energy. Okay, and there's one of those on there as well. Okay, so that's what we've been working on for the last few days, EI equals EF. Okay, write out your mechanical energy initial, your mechanical energy final, see if any of them are zero. Okay, plug in your formulas, probably cancel mass. Okay, manipulate and solve. Okay, and then the one thing we haven't talked about yet that we're going to talk about on Monday is efficiency.
We're gonna talk about efficiency right before the test, because it's on Tuesday.
Your test is on Wednesday.
You need to remember.
We're doing a lab on
with
Tuesday.
dates.
Yeah, okay? All right, so for efficiency, okay, like I said, we haven't gone over it yet, but it's a pretty straightforward concept. Okay, it's the percentage of the energy input that actually does useful work. Okay, so if I use 100 joules of energy, but I only manage to do 50 joules worth of actual work, then I'm only 50% efficient. Okay, that kind of makes sense? Basically, efficiency is just calculating a percentage by taking how much work you did and dividing it by the amount of energy required to actually do it, okay? And then you get your percent efficiency. All right, so we'll talk about efficiency. We'll talk about some examples of efficiency and stuff on Monday, okay? So 20 multiple choice, 7 written, then let me double check, make sure those numbers are right. Okay, yes, 20 multiple choice, and yes, 7 written response. Okay, all the formulas that are on the back of your periodic table, as well as any other useful numbers like G being 9.81 and things like that, are all on the front page of the exam. Okay, so they'll all be there. That means you don't need your periodic table, nor should you have said periodic table, because I'm not checking them over. Okay, I'm just giving you the formulas on the front of the test. Okay. All right, so in the multiple choice, work and energy, types of energy, thermodynamics, systems, thermodynamics, vectors and scalars, V equals D over T, calculating displacement, final position minus initial position, graphing, acceleration, energy, energy, efficiency. Okay, for the written response, graph, acceleration, graph, work and energy, work and energy, conservation of energy, acceleration. Okay, anything you would like me to cover in more detail?
Do we need to know like the scientists and their, like, what they did?
No. You need to know the types of energy though. That's the second, first one. What else, guys?
All the answers to the multiple choice.
Okay, the answers to the multiple choice are A, B, C, and D. You can choose. One of those will be right on every question.
Okay, calm down.
Do you see the sarcasm dripping off of him?
Wait, what?
It was a good try. It was a good try.
Okay, you guys want me to put a few questions on the board for you to try, review questions?
Yeah.
Okay.
Okay. That's all we can say.
Okay, try that one.
All conservation energy.
No, it's acceleration.
It's an acceleration question. Okay. So, it would be a conservation of energy question if I was given a height. Because I'm not given a height, I can't use conservation of energy. Okay? But I'm given a time, also something I'm never given in a conservation of energy question. Okay? I'm told that it falls off. Okay? Okay, and I'm looking for final velocity. Okay, so A equals VF minus VI over T. Okay, we're manipulating for VF, so multiply both sides by T. VI is 0 anyway, so I'm just going to get rid of it. Okay, T times A will equal VF. Okay, so 8 times 9.81, 78.48. Meters per second. Yeah, negative or downwards, down. Oh, what, didn't I just tell you that? Now you know why I make such a big deal out of it.
Brady, yeah, I was wrong. Right.
Negative would work. Honestly, on that question, so many of you will forget to put the direction on that I will basically take anything that implies it was not a scalar quantity. Unless it's up. That's wrong.
What if it's like east?
No. It has to be something implying down on that question.
South is down.
South is down. Yeah, you
Well,
never know.
technically,
It'll depend. If we're up to 24 people out of 25, I can put a vector on and you put east, I'm gonna go, yay! You're way off and I'm never using you as a guide, but okay, you remembered it was vector. All right, so we had a request for a graph. There we go.
Oh. What are you trying to find?
Okay, here's what I would like you to calculate using this graph. First, what is the velocity of this object?
2.7.
Meters per second, yeah, positive, okay? I would probably on a graph like that, now maybe I would do something like this.
Oh.
I don't like that. Can we not do
You
that?
gotta watch on the axis. If it's a vector quantity, the axis can be where you can find the vector.
I'd cry
Eh?
if you did that thing.
Let me ask you,
No, like when I get
That's
that.
true. Unless I do this. What is the position of the object after 30 seconds?
then that's not fun.
Oh, I don't care about your fun.
I miss bio.
Would it just be 2.7 times 30 plus 40?
Plus 0.309, right, okay, so that's a
east
y.
after.
That's a east, right, okay. So this would be a y equals mx plus b calculation, so we would have 2.7 times 30 plus 0.309, okay? And you would get your number, okay? What if I asked how long it would take to reach 50 meters?
Eventually.
I put 50 in for y, I'd be solving for x. Okay, so x would be y minus b over m, so that would be 50 minus 0.309 divided by 2.7, and that would tell me how long it takes to get to 50 meters. Okay, simple y equals mx plus b manipulations, just like you were asked to do on your laps. Okay? All right. Everyone okay with that?
I wish to know which number is which letter. Why are you being such a judgy Jew?
I would like to know the following things, just so you know where all these happen. This is at 5 seconds. And this is at 7 seconds. I think the rest are pretty clear there. Okay, this would be -4 right here. Okay, and this would be probably 9.
That's 8. Yeah. That's it.
No. No, it would have to be, well, I'm going to say it's 9. I get to be right, it's 9. Okay? Yeah, it would have to be 9.
Yeah.
6, 7, 8, 9. It's got to be 9. Okay. I would like the total displacement of this object over the full 9 seconds. I'm not here to be liked.
I got it. We're still homies.
Okay, so we got -4 times 2 divided by 2, so that should be -4. Okay, then we got this one here that is 3 seconds on the base, 9 high, 3 times 9 is 27, divided by 2 is 13.5, positive. Okay, this one here is 2 seconds by 9, so that's 18. And then we got this one here that, oh, did it shift over or something?
9 by 2.
Okay, so yeah, 9 by 2 divided by 2 is 9. Okay, meters. All right, so 27, 40.5, and -36, or sorry, positive 36 meters.
I don't remember what I said.
36.5, sorry, 36.5.
Did you ask for the total displacement?
Yeah, but one of them is negative.
Right. That'd be the total distance if you added the
Right, if
total.
it would be total distance, if you had 40.5, it'd be total distance.
Started with 3.
Okay, ringing a bell? Okay, one other thing I could ask off of this graph. What is the acceleration between 2 and 5 seconds?
3 meters a second.
5?
I don't know, it's got to be yeah, 3 meters per second, 3 meters per second squared. And it should be positive also. Okay? All right.
9 divided by 2, right?
I'd like to know your answer's not.
Okay, what's that showing?
Hot and cold with a rectangle and there's an arrow pointing right.
Heat engine.
Oh, it's one.
Which uses the what law of thermodynamics?
First,
Second.
second one.
Third.
Third
1 through 5.
one. One of them. Even one of them.
Second one.
Second law of thermodynamics is energy always flows from hot to cold. First law is the conservation of energy. Okay, so this is showing second law of thermodynamics. Okay, if we're wanting to harness that in a heat engine, obviously the hot part and the cold part need to be separated. The engine's in the middle. Okay, as matter moves with energy, it can do useful work and be converted into other things like mechanical energy. Okay.
Isn't that one we went with the dumb boat idea?
Yes, that dumb boat idea.
I like the dumb boat idea.
Okay,
Jackson would be the one to.
try that one.
one.
That's my scary roller coaster. Okay.
Pretty steep.
The first hill, I don't know how high it is. Okay, but I know the roller coaster is moving 5 meters per second. A little while later, it's 8 meters above the ground and moving at 21 meters per second. Calculate the height of the first hill. So, conservation of energy question. Initial energy equals final energy. Okay, mechanical energy is potential plus kinetic.
I got 29.
Okay, any of those zero?
No.
No. All right, so we got to put in, we're looking for H initial, so that means we're looking for something that's part of this, so I'm going to subtract EK over to the other side.
I did 8 instead of 5. You don't. I did 8 meters per second instead of 5 meters per second. Yeah, I deserve to be called.
Minus EP. Okay, watching up here, please.
Almost lost me.
Right, so we got MGHI
That's right.
equals MGHF plus 1/2 MVF squared minus, that's supposed to be EKI, 1/2 MVI squared. All right, M is in every term and I wasn't given it anyway, so it cancels out. Okay, I want to divide both sides by G, that'll give me HI. Okay, plug in my numbers, and I'm looking at 9.81 times 8 plus 1/2 times 21 squared minus 1/2 times 5 squared divided by 1/2. meters. Okay. It would just be 29 because we only have 2 Actually, it would only be, it would be 3.
Careful consideration. I have.
3 times 10 to the 1. Okay, if we were doing that with significant digits.
I like these questions now.
Okay. Well, they're patterned, right? Once you know the pattern, they're not hard.
I'm bad at getting the
Okay.
pattern.
All right. Any other questions?
I really like the pattern graphs.
I have a question about, so for, position versus time graphs.
Yep.
Is the acceleration, would that one be curved down or would that one be
On a position time graph, it's definitely a curve.
Okay.
Okay, here's, and just for an explanation, here's why. Okay, on a position versus time graph, the slope of a line is the velocity. So if the velocity is changing, that means the slope of the line has to change. And a curve is an ever-changing slope. Yeah? On a velocity time graph, if you get a curve, it means you have a non-uniform acceleration. We have never dealt with that. So.
And the way you can tell the difference between conservation of energy and a work energy theorem is just one talks about force and distance, the other doesn't.
Well, and in your work energy theorem problems, only one kind of energy would change. A conservation of energy problem has to give you heights and speeds,
Yeah.
whereas a work energy theorem would only give you one or the other.
That makes sense.
Right. But yes, it would also have force, distance. You don't get force and distance in a conservation of energy question. Okay, what else? Okay, well, you still got 6 minutes left, and you have that review sheet that I posted. You could have a look at that. Maybe do a little bit of study, and then the last 6 minutes here. Okay? Use our time effectively.